I will, let me see, I have to stop share. And Andy, you can share your presentation.
Thank you, Thomas and Maxim, for the invitation, and thanks to all the organizers of the CMDS webinar. This will be a great way to stay in touch. I'm going to talk about applications of action spectroscopies to layered perovskite systems. So first I'll tell you about the systems and their electronic structures, and then I'll talk about studies of relaxation mechanisms with conventional methods, and then finally finish discussing applications of action spectroscopies to photovoltaic devices. Layered perovskites are quantum wells composed of perovskites with special properties. They have large absorption coefficients, large exciton binding energies. They're moisture resistant, and they are being employed in applications to light emitting diodes and solar cells. This slide describes the structure. This is the bulk perovskite. Each of these green squares, that's a top-down view of lead iodide octahedra. In the layered perovskites, these organic molecules, phenylethylammonium and butylammonium, for our applications, still fill the spaces between the quantum wells. That thickness of that organic layer is approximately 1 nanometer. And the perovskite quantum wells can form in a number of ways. You have here an index representing the number of stacked octahedras. So we can have 1 or 2 or 3, and we keep going. So this figure represents the electronic structure versus position. The point is that these organics, they don't absorb visible light. They're transparent to the light we're using in the experiments, whereas the quantum wells will interact with visible light. So we are studying these systems, and the organics are serving as insulating layer. One of the prominent aspects that you'll see in the optical response is the dominance of excitons. In the layered perovskite quantum wells, the bonding energies are quite large, ranging from 200 to 400 milli electron volts for the smaller quantum wells. And there are a couple of reasons for that. One is the dimensionality. There's a stabilization of the exciton by approximately a factor of 4 because of dimensionality. Also, the two-dimensional systems have smaller dielectric constants. So there are a couple of reasons why the excitons are so stable. This is the absorbance spectrum of one of our films. So you can see here excitons associated with quantum well 2, 3, 4, and 5 will be down here. Another interesting aspect of these films is that the quantum wells have different concentration profiles. So the smaller quantum wells will concentrate near the substrate, whereas the largest quantum wells concentrate near the interface with air, and that will influence the relaxation processes. So we've characterized those profiles using ion beam milling. We can drill or mill into the film, create these areas with different depths, which can be measured, and then with a microscope measure absorbance spectra. So optical density is changing, but also the line shape depends on the depth because of the differences in concentration profiles. So we can fit those spectra, and then with the integrated area, determine the relative concentrations of the quantum wells. So I'm showing here let's see, we're milling from the air side of the film. Okay, so this is the fraction of quantum wells that have been removed. And you can see smallest quantum wells, 1 and 2, but they are not found in the top 100 nanometers on the film. But this thickness is about a total of 500 nanometers. So about 20% of the film would find very small concentrations of those smaller quantum wells. So that's important to understand for interpreting signals. So these quantum wells, but they have electronic structures depending on their thicknesses. The largest band gaps, which are represented here, are found in the smallest quantum wells. The band gap decreases with the as the index of the quantum well increases. So for that reason, there will be an electron or an energy transfer cascade that goes left to right. There is also an electron transfer cascade going left to right. The holes, there's not a consensus about in which directions those will move. In a type 1 alignment, as I'm showing here, holes move to the right. But a type 2 alignment, it's also possible holes can move to the left, and it's even possible that there are mixtures of band alignments in these samples. Okay. But yeah, so we're expecting both charge and energy transfer cascades based on the alignments of the band gaps and energy levels. So of course, those are things that we can measure with laser spectroscopies. So I'll talk about first, we start with conventional measurements to determine the rates. So here, this is just conventional measurement, a tunable pump and a broadband probe. And by fitting the spectra, the global fitting method, we first obtain ray constants for the energy transfer processes and the various deactivation processes. So these are transient absorbance spectra acquired at 2 different times, at 1 and 500 picoseconds. And even without fitting, you can see the difference here. The intensity is shifting to the red. That's a signature of energy transfer. So it's a signature of energy transfer. Also, we've fit the data with a model in which each of the quantum wells is treated as 3-level system. So these resonances between the ground state and singly exciton states, of course, these are responsible for the peaks with negative sign. Peaks with positive signs are associated with the resonances between the singly and doubly excited states. So we fit the data, right, with a common set of parameters over a number of delay points, and then obtain ray constants. But there are a number of things happening in these systems. In addition to energy transfer, you have a variety of deactivation processes. It's helpful to inspect the line shapes from 2 dimensions. And we're doing this with a color tuning approach. We're looking at things that take hundreds of picoseconds to nanoseconds. So, of course, that time scale is long compared to pulse durations. So the pump axis we're obtaining simply by tuning the color. So these are 5, in the experiments we use 5 nanometer widths, we just tune across that range, so that's automated in the instrument. And then the probe axis is obtained by dispersing the light on an array detector. In 2 dimensions, you can see the individual exciton bleaches, quantum well 4, 3, 2, and each of those bleaches is accompanied by a blue shifted resonance representing the transition between excited states. So these features with the red contour. As the delay time increases, the signal intensity accumulates over the diagonal. So you can see here, this cross peak grows on the time scale of energy transfer from quantum well 2 to 3. Later, we can see other peaks grow in So this is a 2 to 3 and then a 3 to 4 transition. And then we also see sequential processes over here for the 3 to 4 to 5 transitions. So two parallel sequential energy transfer processes. And of course, that's consistent with the energy funneling picture originally predicted for this system. I'll also point out here that excitons are dominating the responses. They have narrow line widths, large transition dipoles, and so we cannot see much of the response coming from the continuum states in the semiconductor. So the information is limited in that sense. But nonetheless, we have a lot we've learned from conventional transient absorption. Each one of those energy transfer steps, that takes around 100 picoseconds. Overall, the energy funneling process continues for approximately 1 nanosecond. And in these larger quantum wells, we're finding exciton dissociation. They have smaller binding energies beginning in quantum well 4. Those signatures of exciton dissociation become prominent. And then in parallel with those dynamics, you have deactivation at edge states, radiative recombination. So we're finding roughly 50% of the excitations relax by some other way than energy transfer. Okay, so based on these measurements, it's hard to say what those alternate relaxation mechanisms are. And that is what has gotten us interested in applying action spectroscopies. As we've heard today, in action spectroscopy, a spontaneous process of interest is detected instead of measuring coherent light emission, for example, photocurrent, fluorescence. And what we like about this technique for our applications is that the relaxation dynamics are specific to a phase of an excitation, whether it's photocurrent production or spontaneous emission, because we have many relaxation processes happening in parallel in the layered perovskites. So this slide also addresses the motivation. So transient absorption, we're seeing everything, right? Every species weighted by its concentration and extinction coefficient. So there are some things that are hidden, but by measuring fluorescence, which we will detect in the near infrareds, that'll be emission from the largest quantum wells. We obtain information that's specific to processes that transfer energy to those thickest quantum wells. So we don't see anything else. Whereas in photocurrent spectroscopy, we can target specifically electron diffusion and electron drift. Right? It's important to understand those processes for insights into the applications. So this is the setup we're using to collect these data. So we're doing this with 2 pulses, so not a Fourier transform. Again, we're looking at dynamics that are hundreds of picoseconds, and then we'll even look out to many nanoseconds in these experiments. So we have 2 pulses, they're both color tunable, and we have control of the delay, of course, and we're applying this to a photovoltaic device based on the layered perovskite. So through the photocurrent channel, we obtain 2D spectra just by wavelength tuning. So we can obtain those as function delay as well. And from the fluorescence channel, we obtain 2D fluorescence signals. And from the perspective of the device, of course, this is useful to have both pieces of information because they represent the productive and lossy processes in the device. So first I'll tell you about the fluorescence spectra. This spectrum is again like the transient absorbance data dominated by the excitons. You see the diagonal peaks representing quantum wells 3 and 4. off diagonal, we have cross peaks that arise because of transition dipole couplings between the quantum wells. Those transition dipole couplings, they're on a similar order of magnitude to what you would find in a photosynthetic protein or molecular aggregates. We see many of the same spectroscopic signatures. Also, this is interesting. The measurement, it's producing a different pattern of peaks than we find in transient absorbance. For example, the quantum well 2, we don't see any contribution. Okay. I believe that is because that's one of those quantum wells that's concentrated near the substrate. So I believe that this may represent the poor overlap in the concentration profile for that smaller quantum well and then the larger quantum wells from which you're detecting emission. So pattern of peaks is a bit different, right? But we can still see signatures of energy transfer. This is the transition between quantum wells 3 and 4. Okay. It's that's appearing on the same time scale we observe in transient absorbance. Okay. At later times, again, we can see the signature of the sequential processes, the growth of this cross peak between quantum wells 3 and 5. So the data are showing that those peaks are generated on same time scales in transient absorbance and in fluorescence spectra, which they should be. The pattern of peaks is a bit different. We're also seeing a broad, you can see there's a broad contribution that these excitons are sitting on top of in the fluorescent spectra. And I believe that comes from the direct excitation of the continuum states in the largest quantum wells, because it'll be an efficient process to directly excite those continuum states. The carriers relax and then radiate in the near infrared. So there are some differences. The photocurrent spectra look much different. We have broad line shapes consistent with the continuum states. So those are the resonances that are difficult to observe in transient absorbance. There's also a contribution from the exciton, for quantum well 4. Right? That's the quantum well where we start to see prominent signatures of exciton dissociation. So it makes sense that it contributes. At 500 picoseconds, this quantum well 4, its signal strength is decreasing. At 2 nanoseconds, that resonance has really decreased quite a bit. And we're also seeing something interesting, which is the redshift in this part of the spectrum. Okay. So for this system, again, the electron transfer cascade, we expect that to go from the smallest quantum wells to the largest quantum wells. So that is consistent with the signature of electron funneling that's predicted with this system. So I can zoom in on the temporal profiles. So I'll show you here quantum well, it's cross peak between quantum wells 2 and 3, 2 and 5. Okay, so quantum well 2 to 3, where that contribution is enhanced, we find slow decay. Whereas for quantum well, for the cross peak between quantum wells 2 and 5, we're seeing this delayed rise. Okay, so the time scale of that rise, that rising contribution is growing in as you move up into this area of the spectrum. Okay. And that's consistent, again, with electron funneling between these quantum wells. So that's interesting, right? That is one of the motivations that originally motivated the use of these systems in photovoltaic devices. And so we want to understand, right, is that important? But it's hard to say based on what we have here. The data is chopped off at 3 nanoseconds, and it's also not clear how these various pathways compare in their efficiencies to photocurrent generation. So that's motivated our most recent experiments in which we're targeting the carrier mobilities. So in these experiments, we're going to make the active layer of the device thinner, okay, and also we've increased the delay range to 15 nanoseconds so that we can see more of what's happening in the active layer. Right, so this is a sketch of the device. You have a whole selective layer on the left, electron selective layer on the right. So in this experiment, the pulse 1, right, initiates the drift of that electron. We probe the carrier with pulse 2, but that will be at a different position. The displacement is the product of the delay and drift velocity. And then the carrier will continue to drift until it reaches the transport layer. So because of the way the electron and hole selective layers are arranged, the electrons will move left to right, the holes move right to left. And this total distance, that is 110 nanometers. Okay, so we're thinking about what does the temporal profile of the nonlinear photocurrent signal represent physically. Okay. So we know pulse 1, right, that produces a photoexcited carrier concentration in the active layer, and those carriers will relax, right? The signal decays when those photoexcited carriers are removed from the active layer. And that can happen for a number of reasons. Carrier drift we're interested in, but also we have excited state deactivation. We can have spontaneous emission or defect-assisted recombination. There's diffusion. But also charges can accumulate near the transport layers in devices, and that also influences the temporal profile of the signal. So in order to detect the drift of the carrier, which is what we care about, so the drift, okay, so the time scale on which we're that dynamics, the time scale on which we're expecting those dynamics is ratio of path length to drift velocity. Right? So really what we're interested in is finding drift velocity. So the way to do that, of course, is to vary the external bias in the solar cell, okay? Because the drift is sensitive to that external bias. So this is the point for quantum well 3. Okay. So we vary the external bias, and then in that way control vary the drift velocity, and then through a weighted average of time constants, compute those velocities, plot that against the electric field in the active layer, and then fit that to a straight line. The slope is the carrier mobility. Okay, so there are other methods of determining carrier mobilities in devices, but they use a similar approach. Okay. The mobility obtained in a device, right, if you keep in mind, right, it represents what's happening in the material, but there are also device contributions to that mobility. Right. Mobility is measured in devices, typically 10 to 100 times smaller than that measured, for example, by photoluminescence quenching outside of a device. But I still think we can use the technique to understand better what's happening in the active layer. So here is a signal with pulses tuned into resonance with quantum well 4. Okay, so we're enhancing the signal component representing transport in that phase of the film. So what you see, first of all, within 15 nanoseconds, most of those photoexcited carriers have been removed from the active layer. Right. Also, we obtain a mobility, which says that the carriers are responsive to the electric field. At quantum well 3, right, we're also seeing that again, most of the photoexcited carriers are removed from the device effectively within 15 nanoseconds. The mobility also quite similar, comparing quantum wells 3 and 4. Right? So these are the quantum wells with intermediate sizes. So we expect this phase of the system to span that full distance between electron and hole selective layers. And so these are in principle the best quantum wells for transporting the carriers. And so back to this signature of electron funneling that's observed really everywhere here above the diagonal. Okay. It's most pronounced in this cross peak because of the large difference in the indices of the quantum wells. So what you see here is I'd shown earlier that we had detected the rising component of the signal at the 3 nanoseconds. And now we have data going all the way to 15 nanoseconds showing that the concentration of photoexcited carriers is decreasing after 3 nanoseconds, but not very much. At most, 20% of the photoexcited carriers have been removed from the active layer. Right? In addition, in this region of the 2D spectrum above the diagonal, right, particularly up here, with detection when the second pulse is at a wavelength longer than 640 nanometers, okay, we find that the profiles are independent of the external bias. So the mobility is 0. That is a signature of trapping. Right? That may also reflect the overlap in the concentration profiles of quantum wells 2 and 5. Right? Because quantum well 2, that's one of those quantum wells whose concentration does not span the full active layer of the device. So I can summarize what we've learned. We've detected carrier funneling and energy transfer funneling as had been predicted for these systems. We're finding that in the photovoltaic devices, carrier transport is primarily occurring in the phases of thicker quantum wells, the most concentrated quantum wells who span that full thickness of the active layer. The smaller quantum wells appear to function as debris. There is a carrier funneling process, but it doesn't appear to contribute much to the photocurrent. Right? Secondly, these smaller quantum wells, they have large absorbance cross-sections, but they're also likely to relax by spontaneous emission, so that's not helpful either. Okay. And as to the technique, I think that this shows that the charge transfer trajectories can be distinguished with nonlinear photocurrent spectroscopy in a system with a heterogeneous active layer. So this particular system is very well suited to the technique, but there could be others. For example, organic photovoltaics have multiple components in the active layer. And I'll thank the other people involved in the work. Our collaborators, Wei Yu, Jun Hu, Ming Yan. They are experts in making devices, but they've also been very helpful for interpreting the experiments. So we couldn't have done any of this without them. And our research group, Ninghao Zhao, Zhenyu Oyu Yang, and Mac McNamee conducted the action spectroscopies and developed the most recent application where we're determining carrier mobilities, whereas Olivia and Jenkun were involved in the transient absorbance and in the original setup of the action spectroscopy experiments. Okay, so that's all I have. I thank everyone for your attention, and I'll be happy to answer any questions.
Thank you very much. I am sure that there are questions, so please just drop a line that you have a question in the in the chat session if you have a question.
Yeah, well, I see that Marek Manfro has a question again, right? At least I see the line. No, okay, yeah. Right, Artyom, go ahead.
Andy, thank you very much for the talk. I really like this type of spectroscopy. But maybe it's a stupid question, but it's not very easy for me to keep in mind all the effects in photocurrent spectroscopy. So what is the main? You have two excitations, first excitation and second excitation. What is the main effect? What is the mechanism? How the first excitation affects the total charge, basically the total current being collected from the second pulse?
Okay, thank you for your question. So the first pulse will photoexcite carriers in the active layer. Okay, those carriers drift. The second pulse interacts, but not with 100% efficiency. So then we essentially, that nonlinearity would represent maybe 5% or actually probably even much less, maybe 1% of those photoexcited carriers who were, who interacted with pulse 1 will interact with pulse 2.
Do I understand correctly that basically you'll have some kind of a bleach of the states? Basically, it will be just effect on absorption. You will absorb less photons from second pulse because some of the states will be already populated by the first pulse.
Yeah, so in this experiment, we have ground state bleach, excited state emission, and excited state absorption like signal components, so just as you would find in a transient absorbance experiment. Okay, so, so the information content is similar, but we're only observing signal components that represent contributions to the photocurrent. So, so I believe it's helpful to think as about the information as being comparable between the transient absorption signal component. Go ahead.
I think I got your answer. Thank you. And would you consider also a fact that by changing the concentration of carriers, you can promote, I don't know, bimolecular recombination? So some effects which are not like purely optical in the moment where your pulse arrives, but you will have effect of carriers interfering later in the device.
Yeah, I'm not sure I understand. There certainly are intensity-dependent recombination effects, and we've also characterized those with transient absorbance microscopy. So those effects are actually quite prominent in the films processed via solution. So we do expect that to happen in the device. However, that component will be insensitive to the external bias. So that is with these profiles alone at one value of the bias, right, there are many contributions that are difficult to separate. So by varying the external bias, we can target the information we're interested in.
Okay, thank you.
Okay, thank you. Didi, go ahead, please.
Hi, Andy. So I'm wondering if, so in the fluorescence 2D experiment, you are sensitive to the excitons which recombine and photoluminesce. So I'm wondering if you do an experiment with a fluorescence 2D experiment, but with application of bias, do you think that could inform about local dielectric constants? Because you're basically mapping out the fluorescence generated, and I guess I'm bringing in spatial resolution here, but do you think application of bias, a gradual increase of bias, and then performing fluorescence 2D experiment could be helpful that way?
Yes, thank you for your question. Yeah, in fact, we've tried to observe an effective bias on transient absorbance signals and find no effect in this range of the bias. It's possible that applying larger biases, maybe we will see something. But again, the fluorescence and transient absorbance responses are dominated by the excitons and not the free charge carriers. So it may not be so sensitive. But we have not tried that yet with the fluorescence detection.
Okay, so but I guess my question is, in fluorescence detection, whichever energy transfer process happens, ultimately the excitons that recombine give us the signal, whereas in a transient absorption experiment, if I'm understanding correctly, one is also sensitive to, let's say, states which have undergone charge separation, right? Like the third order polarization for those states would still contribute to the signal, whereas in a fluorescence detection experiment, one is not sensitive to those states.
Well, in the transient absorbance and fluorescence, we're sensitive to the responses of the excitons and energy transfer processes. It's possible that you could have an energy transfer cascade and do like a thick quantum well, the exciton dissociates, and then that contributes to photocurrent. But that type of process, we should be able to detect through the photocurrent as well.
Yeah, I guess my question is, like, if you apply a bias, how does the fluorescence 2D spectra change? Because
we have not tried that, but we have tried to vary the bias and detect transient absorbance signals, and we see no change at all.
Okay, thank you.
Okay, Tono, I see that you are unmuted. You're going to ask a question, right?
I would like to ask, yes, indeed. I was thinking about the possibility of a scenario for fluorescence that charges are separated, but they recombine in the larger or thicker layers afterwards. Can that happen?
Yes, I think that is happening. Let me go here. Okay, so these are the 2D fluorescence spectra. So in these spectra, we see a broad contribution that is not observed in transient absorbance spectroscopy. So I think what's happening there is that the continuum states of the largest quantum wells, which span the full visible spectral range, there's directly absorbing light. The carrier is relaxed to within the phase of the thickest quantum wells, and then they emit light. So there's a component of that signal that represents just direct photoexcitation of the thick quantum well from which you're detecting emission.
Right, thank you.
Okay, more questions?
Yeah, can I ask a question?
Go ahead.
Thanks.
Pavel.
I have a question about the relation between the energy transfer and the charge transfer. So to what extent do they come from the same excitations? And yeah, so in a sense, like you then show that, for example, for the charge transfer, the small quantum wells are not so important, but also you had quite fast, efficient transfer from the small quantum wells to the larger ones, right? So like, is it possible that the same excitons are excited and they dissociate and move, or yeah, what is the relation between the two?
So the probability of dissociation will increase with the thickness of the quantum well. From the smaller quantum wells, we're observing both energy and charge transfer cascade, but we're not finding that much photocurrent arises from that type of process. And I think that may represent the concentration of those smaller quantum wells, on one side of the active layer. Right. So
okay,
we need a
spatial
phase.
energetic aspect then. Sorry,
what's that?
It's a spatial energetic aspect then.
Yeah, so the smallest quantum wells don't span that full active layer. Right? So those responses, like in within the active layer, they're representing dynamics that are close to the electron or to the whole selective layer. Okay, so it appears that the excitations cannot make it out of that domain and produce current very effectively.
Thank you.
Okay, more questions? Thomas, you would like to ask something, right?
You want me to ask a question?
I want you to ask a question.
Well, so I got a bit triggered by the question of atom, actually, because I'm kind of thinking about what is really happening when you do these two excitations and then you measure the charge, right? So if you there must be some kind of in order to see the cross peaks here, there must be some interaction between the two excitations that you bring on in two different quantum wells. So could there be effects like from non-dimensional recombination that you say make an electron somewhere and it's transported to somewhere else and annihilating the hole somewhere else, and not a hole that you created somewhere else?
Yes, I mean, I think that type of contribution would produce an overall decay in the signal, but well, actually, you know what? For like, we're talking about photocurrent spectroscopy, I believe. So in a photocurrent spectroscopy, I don't believe that type of process would contribute to the photocurrent because there's recombination. So,
but you would, well, you would, by that interaction, you would still kind of make a lowering of the signal compared to if there were no interactions between the two pairs of electrons and holes that are created. So my idea here is it could be somewhat similar to what is happening when you have exciton-exciton annihilation, giving signals in the fluorescence detected signals. If it were only,
I see. So you're
but
saying,
I don't know if there would be. It would be interesting if there were like a way of disentangling this from this kind of spectroscopy, and I don't know.
That's interesting. I'm not sure if I fully gather what we're getting at, but so you're saying there could be a component of the signal sensitive to drift, but also where you would have a decay process. The intensity dependent effects, like the so-called bimolecular recombination effects, those dominate on the 10 to 100 picosecond time scale, right? So we can study those directly in microscopies, but we're looking at dynamics that take many nanoseconds. So I think there's going to be a separation in time scales.
Okay, thank you.
Okay, more questions? If not, shall we thank Andy again?
Yeah, let's thank
for
Andy.
Thank you.
Thanks a lot.
And well, what shall we do now? Shall I? Well, first of all, I would like to stop the recording, right?